Building large-scale software requires rigid architectural planning. Without a concrete methodology for organizing thousands of moving parts, even well-intentioned systems will collapse into chaos. To prevent this systemic failure, engineers rely on design methodologies. One of the earliest and most heavily utilized of these frameworks is function-oriented design. The core philosophy of function-oriented design is strict categorization by action. Instead of organizing a system by the entities that exist within it, the nouns or objects, the system is designed entirely around what it must do. It focuses exclusively on the verbs, the functions. This diagram illustrates the absolute basic building block of the methodology. Every task is reduced to a linear sequence: input, process, output. Data is merely raw material, pushed into a function and transformed through processing to become a final product. By forcing every requirement through this lens, function-oriented design takes chaotic, overlapping computational requests and turns them into an ordered, highly predictable assembly line of discrete tasks. The primary mechanism engineers use to build this assembly line is functional decomposition. Massive, monolithic computational problems cannot be solved all at once. The human brain cannot hold thousands of interacting logic loops in active memory. The solution is the top-down approach. An engineer looks at the entire software system as a single massive whole, and then progressively divides it into smaller, specific submodules. It operates exactly like organizing a massive music festival. A single director cannot manage every detail, so the workload is delegated by function to specific, isolated teams. One for security, one for food, and one for staging. This division continues downward, branching out again and again. The process stops when a sub-problem is narrow enough to execute as a single atomic task. Functional decomposition guarantees human engineers can isolate, comprehend, and manage large-scale algorithmic complexity. We can observe exactly how this architecture is constructed by applying it to a recognizable engineering test case, developing the software for an automated teller machine. This diagram represents our starting point for top-down design. We treat the entire overwhelming ATM requirement as one massive unsolved block. We perform our first tier of functional decomposition. The monolith is split into its core operational functions: authenticating the user, checking the balance, withdrawing cash, and depositing funds. While these new modules are smaller, a task like withdraw involves too many variables to be coded as a single reliable script. It must be broken down further. We execute a second tier of decomposition specifically on the withdraw module, splitting it into validating funds, dispensing cash, and updating the final balance. These final bottom-tier submodules represent atomic functions. They do one thing and one thing only, making them simple enough to translate directly into code. This hierarchical mapping perfectly isolates complexity. Different engineering teams can now build, test, and fix the authenticate module and the dispense module simultaneously, without any risk of causing a total system failure. In software engineering, this completed hierarchical tree has a formal name: the structure chart. The structure chart operates on a strict rule of hierarchy. The highest level modules do virtually no processing themselves. They act strictly as traffic controllers, delegating the actual work to the lower-level modules. Looking at the completed structure chart, we see call relationships. These explicit directional arrows dictate exactly which module has the mathematical authority to activate another. The chart also defines data flow. Specific variables, like an account ID, are passed from a parent module down to a child module for processing. Once the work is done, the data flow makes a return journey, where the child module sends the resulting answer back up the chain to the parent. Finally, the chart establishes control flow. illustrating the strict left-to-right sequential order in which these functions are executed. The structure chart acts as a rigid mathematical blueprint, dictating exactly how, when, and where data moves through the software architecture. With the blueprint complete, the theoretical design transitions into the practical reality of algorithmic implementation. We can isolate the withdraw module in this code editor to translate it. Proper decomposition guarantees that the underlying logic becomes incredibly simple to write. The inputs we identified in the structure chart directly become the strict parameters required for the function signature to run. Relying on the modularity of the system, this function doesn't calculate the user's money itself. It simply calls upon an entirely separate module to check the balance. The algorithm then executes the core sequential logic and decision-making process required to validate the withdrawal and dispense the cash. Finally, the code executes the last required subtask, calling the update module to finalize the math. Because this module is highly isolated and performs a single purpose, its algorithmic execution time is highly efficient, often operating in constant time, or O of 1. By strictly adhering to the structure chart, complex software requirements are reduced to a series of isolated, mathematically sound logic statements. Function-oriented design established a standard for early software engineering, offering the clarity needed for small to medium procedural projects. Its modularization makes debugging nearly frictionless. If an ATM dispenses the wrong amount of cash, engineers don't have to search through millions of lines of code. They know exactly which isolated module to examine and fix. But there is a fatal scaling limitation. As systems evolve into massive, globally connected applications, this architecture begins to fracture and snap under the pressure. The core weakness of this